Okay. Section, equilibrium, and section properties. So now we talked about how we figure out the axial force in the bar, and we talked about what are the measures of the formation of the bar. And now what we're trying to understand is figuring out how the axial force in the bar relates to the deformation of the bar. Okay? So let's start. First thing, we start easy. So let's say that we start with a homogeneous bar. So what that means is the bar is made only of one material. All right, so this is our bar made just of one material. And let's look at some section. So let's go to section X. And so let's say that the cross-sectional area is A of X. A of X can change as I move along the bar. It can be skinny, then chunky, then skinny, whatever. It can change. But it's made only of one material, and the modulus, the Young's modulus of the material E, is what relates stress to strain. Okay? That relationship is a relationship that is true at point to point, at every point of a material. The stress at that point relates to the strain at that point if the loading is only uniaxial through the Young's modulus. Okay, so I'm giving you the Young's modulus. And on this section here, we have a strain epsilon axial of X. The strain epsilon axial of X is the same at every spot, because we said that the strain changes along the bar, but it does not change on the section. So if the strain is epsilon axial of X, then at every point on that cross-section, I'm going to have a normal stress equal to epsilon axial of X times E. This is a stress that is going to be the same at every point. So if I take a little area here, a small sub-area of this A, let's call it dA, and if I have a stress sigma n, remember sigma n is force per unit area, on this little area dA, I'm going to have a little force. All this little area is carrying a certain amount of the axial force. How much axial force is the little area carrying is simply equal to the stress multiplied by the little area. Not big deal, right? Great. So guess what? If I want the whole axial force, what do I need to do? Well, I simply integrate over area X the little dn, sigma n dA. OK, I can do that. And sigma n is that thing of epsilon A of X times E times dA. See this thing? It wasn't that hard to get it. This thing is the equilibrium of the cross-section. Is the thing that relates the axial force to the stress. Okay? Now, this is a step that we're going to go over and over in torsion and bending. Now our kinematic assumption pays off. Because see, I need to integrate something over the area. This guy now, does it change from point to point? Does it change? Ah, it's the same. So come out of the integral. I don't need you to be in there. So I can write that n of X is equal to epsilon axial of X. And actually, epsilon axial of X, let me write it instead of epsilon axial of X as dux dx. They're the same, but in order for us to have just the same equation that look just the same in axial loading, torsion, and bending, I like that better. So n of X is dux dx that multiplies the integral over the area of E times dA. Now, E is also constant over the area, and as I integrate it over the area, I get E of x area of x. So this guy here, times du dx. Let's not forget that. This guy here is the section stiffness. This one here is the measure of section deformation. And this thing is the load on the section. So now this relationship connects the force on the section to the deformation of the section through the stiffness of the section. You see? Brilliant. Let's say the other case in which you have a section that's made of more than one material. So let's do number 2. Composite section. And say, just to simplify our life, that there is going to be some part of the section A1 which has a modulus E1, and some part of the section E2 which has a modulus E2. So just to do something like that, I have one part of the section A1 with modulus E1, and then inside here, some other, like the core of this bar is made of something else. Let's say that this is A2 with modulus E2. Let's say that E2 is greater than E1, just for the heck of it. Now, everything that we did here up here still works. My sigma n is still equal to epsilon axial of x times the modulus. But now the modulus is going to be different, right? So for stuff that is here, because the modulus is big, when I multiply the same strain by that modulus, I'm going to get big stresses coming out. In this part here, because the modulus is smaller, I'm going to have a little less stress coming out. You see where this is going? Together, they give me the axial force. But this part here is carrying load in a different way from the stuff around it. There is a core in this bar of stiff things that carry a lot of load. You see that? So now, when I calculate, I do the same thing I did here, and I calculate the axial force, and I do n of x is equal to the integral over the area of epsilon a of x times E times dA. Now I need to split it in two parts. I have to split it. So the cool thing is that epsilon a of x is the same both in this guy, in the outside and in the inside. The section move together. But because the core is stiffer, even if it moves the same as all the guys around it, it doesn't want to move. So in order to make it move, I need to put a lot more stress in there. Okay? So, but the strain is the same. So I can still bring it out as dux dx. But then I need to split the integral over area 1, where the modulus is E1, plus area 2, where the modulus is E2. So out of that, I get now a relationship which is similar to that. It's similar to this one. It's not much different. I get that n of x, if it is a composite, is equal to dux dx times E1 A1 plus, and I'm writing with like a microscopic chalk, E1 A1 plus E2 A2. See, before I only had E times A. I only had one E, one A. Now I need to take into account the fact that I have two materials with two stiffness, and together they give me the effective section stiffness. Okay? So this relationship here, both this and this, you can write it as N of x is equal to du dx times EA effective. So that is the most important equation in axial loading, the very important equation in axial loading. And the way that you calculate this EA effective, if you have just one material, it's just modulus times the area. If you have more than one material, then because when you integrate, you need to split them, you're going to have E1 times area 1 plus E2 area 2. And both of them are into EA effective. You may not know this yet, but the lasagna is done and it's in the oven. Okay? We are done. So let me show you how the lasagna works. Okay, so how the whole path goes. And we're going to just say how it goes. You're going to start working on it. Then we're going to do examples on Monday, all kind of stuff. So 1, you're given loading. You're given the loading. From this loading, we learn how to calculate N of x. Or at least I told you how to. You can do it. 2, I'm given the geometry and the material properties. Out of that, you calculate EA effective at every cross section. 3, you take this relationship here and you invert it, and you get, you invert it and you get dux dx equal to N of x divided by EA effective of x, the one that you just calculated over there. Once you have du dx, you are home free. Because from this du dx, you can do all kinds of things. You can do, out of du dx, you can get epsilon a of x. And from epsilon a of x, which is equal to du dx, you can get sigma n. Because you have epsilon a and you have the material, so you can get the stress everywhere. You can figure out if your structure is going to break or not. Boom. You can integrate epsilon a of x or du dx. Let me write it as du dx. You can integrate du dx in dx over the whole length of the bar, and you get your elongation. You can integrate from where you know to where you want it, dux dx. And you get the whole displacement field. This whole thing that you get here is u displacement as a function of x. You know where every single point of the bar is going. How is that? Great lasagna, I would say. Okay? So this is a very, very good, complete story for axial loading. I'm going to play games with you. I'm going to switch it around. Maybe I'm going to give you u of x. From u of x, you differentiate, you get dux dx. You get the strain, you give the stress. From the stress, you can get the axial loading. I can kind of turn it around. Give you A, I want B. Give you B, I want A. But remember, when you solve your problem, you always go forward. You go forward solving problems. Even if I'm not giving you everything, imagine that you know everything, you follow this path, and in the end you find an equation, and in this equation you put what you know, and out of that will come what you don't know. Okay, so this is it. This is the story for axial loading, and you get on a very good start, okay? You guys have a great weekend. It's the weekend as far as I'm concerned. Okay, bye guys.